the resistance is given then. Every material has resistance. Copper resistance is very low, but it does have some resistance, but mostly copper is a conductor. It would conduct electricity very well, as would silver, which is the best metal conductor. Other kinds of materials inhibit the flow of electricity through them, like glass, for instance. These types of materials are called insulators. So glass is a very good insulator. Copper and silver are very good conductors. Here the potential difference is shown between the two poles in the battery, and batteries have a voltage indicating their rating of energy, the amount of energy stored in the battery. So the potential difference in an electrical circuit is like the height difference here. The height of this column of water is what's supplying the force, the gravity, and I draw these two drums at a stair-step height like this so that the flow of water would be constant once the valve is opened all the way. Nothing in the empty drum resists the flow until the water reaches the very top, in which case all the water is moved from the left drum into the right. So potential energy is probably the hardest thing to understand in electrical circuits, because the potential energy is what's the voltage is measuring. In a battery, there's potential energy stored in the battery, and the difference in that potential is measured by the difference between the positive terminal and the negative terminal. We can then go apply the magnetic property to moving magnetic fields and create a simple kind of AC generator called a magneto. The crank on one horseshoe magnet rotates this magnet through 0 through 360 degrees back to 0 and repeats again. The magneto device was such a device that early telephones had, because the mechanical turning of the crank generated an alternating current that would actually light a light at the central office, indicating that there was a connection requested, and the operator could then close the connection and be able to talk with the person in order to help them complete the call. So here in this experiment we have one fixed and one rotating horseshoe magnet, and a copper wire is coiled around the fixed magnet, and each end is tied to a measurement reading device called a voltmeter. A voltmeter can measure the potential difference between its two poles. As we turn the crank 90 degrees at a time, we notice that the needle on the voltmeter moves. It goes from a neutral position, completely vertical, to being pegged all the way over to the right when the two magnets are attracting one another at both gaps here. Then back to neutral when another 90-degree turn is applied to the crank, and then it's repelling, going all the way in the opposite direction, pegged left, when the two like terminals are facing one another, and then back to 0. So by tracking this sweeping motion through 360 degrees and repeating, we see a sinusoidal pattern, the classic sine wave pattern being exhibited by that needle as it goes back and forth. This is the pattern of alternating current. We turn it on its side, starting it at 0, and talk about the properties of a sinusoid. It has both amplitude, which is the height of the wave, and a frequency, which is the number of complete waveforms we see in one fixed unit of time, like 1 second. We measure signals in cycles per second, and 1 cycle per second is also called 1 hertz, after Heinrich Hertz, a pioneer in the field of electricity and magnetism. The classic sine wave pattern from math and physics course owes it to this model of electromagnetics. Also, a wire moving between two attracting poles of magnets in a magnetic field can generate a change in the magnetic field as well. This is the principle on which electric pickups on electric guitar would work. An electric guitar has magnets below the strings, and when you pluck a string and the string vibrates, the magnetic field underneath that string picks up the vibrations of the string and takes that mechanical energy from the change in the magnetic field property and turns it into an electrical current. That electrical current is then amplified and can be played through a speaker, and you can actually hear the electric guitar string. Once it's amplified, you can hear it at a much louder level because of this electromagnetic effect. The same idea of a magneto, the ability to generate electricity by having movement within a magnetic field, can be used to generate electricity by moving the wire, rotating the wire, rather than rotating the magnets. It's far easier to rotate the wire than it is the magnets. They're much lighter, and we get the same effect. So this is the principle on which most electrical generators work. They have a set of coils, and the coils will rotate through magnetic fields, north-south, north-south, inducing different magnetic fields will induce the electrical current flow. This shown here in this diagram shows a set of 8 wire coils at ends of an armature, and these coils rotate between north and south poles, capturing that magnetic field in the form of voltage carried along the copper wires. The other properties we have with the signals are their frequency, their amplitude, and their wavelength. And this is shown here in 5 hertz or 7 hertz signal. Slightly shorter wavelength here results in higher frequency. And in this 10 hertz signal here, we have the wavelengths being shown, and the amplitudes can also be changed as well. This would be the electrical energy in the field. You know that when the magnets are closer together, the magnetic field will be stronger than when they're at a further distance apart. So at a further distance, we might get 2 volts generated out of a simple generator. If it's closer together, if the air gap is smaller, it might get to be 3 volts or 4 volts or 6 volts, given increasingly smaller gaps between the magnets when we rotate the wire coils through them. Both the electrical analog waveform, shown here as a sine wave on the bottom, and the waveform produced by sound are the same sine wave pattern. And so when we talk about audible sound, we talk about frequency, and the higher the frequency, the higher the pitch. And the higher the amplitude, the higher the volume. And so we have these analogs to sound waves that work very similarly with electromagnetic waves. And a device that converts these different forms of energy is called a transducer. We can actually convert an electrical field or sound into a mechanical sound, and a mechanical sound could also be converted into an electrical sound as well, using the basic properties that we've shown here of magnets and electrical circuits. So direct current is much simpler than alternating current. Alternating current has this continuous change over time. Its voltage is continually changing, oscillating between its plus and minus peak here. Direct current, on the other hand, graphs flat on a voltmeter. It's just constant. And so it actually decays a little bit with time because the battery wears out. But for all practical purposes, when we draw the voltage pattern of a battery or a DC type voltage source, it'll be a flat line. It will not have any curves or shapes to it. Well, that pretty much concludes our first module here on electromagnetics. We'll be investigating other properties in following lectures, and we'll talk about and return to these concepts that we've shown here with magnetism and electricity as we look into the electromagnetic spectrum and the broadcast frequencies for television and radio. And these principles and properties will help explain how some of those other technologies work. So long for now.